It's a great honor to be here to speak to such a spectacular audience. I didn't realize that there are two parallel tracks because I wanted to be hearing also Emmanuel's own presentation, but I will do my best to make sure that this room is equally entertained. As the previous moderator introduced Mike, he produced many graduate students. In fact, I am among one of his graduate students many years ago. It's always intimidating for him to speak after him because he always dive so deeply into the technical content, which makes a good foundation for me to roll out my presentation. I will be stepping a few stories higher to give you maybe a more broader view about what's AI and what is going on in the whole field. In fact, another speech from President Laura was also very interesting. She mentioned about a comment where university may disappear in 3 years with new AI. I took it a slightly different way. I think indeed there needs to be a lot of change in modern universities in light of modern AI, and it encourages you to actually rethink how to reprogram university, and that's exactly what I did in the past few years. So I want to take this chance to also say a few words about a new project I have been doing, which is to create a brand new university of artificial intelligence in a young country called the UAE. Right, so this is what I've been working with in the past 4 years. I went to Abu Dhabi in UAE to be the first president of this university called Mohammed bin Zayed University of AI. It is established exactly 5 years ago, and it is meant to be a graduate school for AI research and innovation. And over the past 4 or 5 years, we actually made tremendous progress in thinking how to create a sensible modern program in AI and beyond that, and also how to build on the success or maybe lessons to do even better. And here is a quick word about where we are right now. Right now, this university has been really doing very actively in expanding. We actually went through a very aggressive path of expansion in the past 4 years. You can see this growth rate, which we kept above 50% every year. And as of now, all the disciplines we covered, which includes 8 departments in different areas of AI, collectively ranked top 10 in the world. And we published, of course, thousands of papers. And we graduated 100 students, many of them stayed in the UAE. And we even roll out many startups and train many government and the private sector leaders. But this university is unique in that it is not about just education and the basic research. We are almost also like an industry where large foundation models, modern AI infrastructures were deployed and utilized and explored and pushed further. And here are just a list of some of these projects. You can see we produced actually the largest and the best Arabic natural language models. And also we've been developing models for biology, for the world model, and many other things. I think that's probably an interesting new approach to modern university where you want to bridge the gap between university and the private sector to make them more agile and also more resourceful in terms of how large-scale modern science in AI can be carried out. Otherwise, university indeed will stay out of the game and become less and less relevant with the fast advancement of AI. And through that effort, we were able to really push UAE to the frontier of global AI competition. One of the rankings published in Stanford last year actually put UAE now among top 5 of the AI power countries. And I believe our university made some positive impact in that ranking. In the next couple of years, we are going to continue to grow, but not only in the space of AI. As Mike mentioned, AI is in fact, many years ago, we don't even call ourselves AI. We call ourselves statistical machine learning and other things, which means that it is a very profound and this interdisciplinary field, which can enable a lot of other topics. And as a university, we cannot just solely rely on a very narrow band of innovation. And our plan is to add both breadth and depth into the offering and also into our activity. For example, in the next 5 years, we're going to add 2 new colleges in public health and in decision science. And after that, we'll be adding back the arts and sciences and also the engineering, but in a way that is different from the way we did or people do nowadays, because these are a vision, as mentioned, coming from the 50s, and now with the AI, which provides you encyclopedic knowledge right next to your fingertip, how can you rethink about the skill? How do you rethink about the innovation? And doing your job can be very different, right? So we want to make sure that our education and the university infrastructure are prepared, maybe even stay ahead of the game to get trainees ready for their job. So with that, I hope I set a stage, for the talk, because the technical material that I'm going to present actually came from our work from this very university, which was actually not quite so possible, elsewhere in the world, in the traditional school, because of resource limitation, because the traditional incentivization mechanisms in university, which counts papers, or counts other things. And here, we're thinking about or talking about how to maximize the impact of AI and how to execute even faster. Right. So, just a quick recap. What is happening now, in the AI world? Well, this is happening. Last year, we got this great, a boost, in our field, which is that, our foundational work and our applicational impacts gets recognized, by, honors, as prestigious as a Nobel Prize. And that actual announcement come right in the middle of my own presentation in a workshop promoting, AI applications in biology. So it was very, very exciting when we heard that news. And not only it is recognized in the AI field, it is also widely recognized in the general public. You see now a wide spectrum of applications of generative AI and large models across the field, in language, in image and video, and in science. People are talking about, maybe the whole way of life will be disrupted as a result of that. So is that true or not? There are obviously a lot of debates, as we already just heard, right? There are, disagreements on what is the AI definition itself, how we do AI, and also how we extrapolate into the future. Some people are very optimistic about AI. They were talking about AI really, leveling up, over the course of development very quickly, in fact, to the point that they may be able to, generate a new civilization, enable organizations, or be, a propeller or catalyst of new organizations down the road through these multiple levels of advancement. Other people, including my colleague sitting right here, were less optimistic because, it is, very, very true that there are a lot of limitations in what we see in the current AI systems, not alone, some of the fundamental flaws in the design and in the implementation. And others, maybe are taking the middle ground. So I want to make this presentation a little bit outside of this debate because we can go on and on without a finishing line. I want to pull back to think about why we care about all these discussions. As Mike just mentioned, somehow AI was positioned, half a century ago by, a very, very famous hypothesis or test called Turing test, which basically, unfortunately sets AI against human. And that's how we define AI. Even though there isn't a clear mathematically rigorous or even quantifiable definition, it's like put 2 people or system and AI system and people behind the screen and do whatever you want to do in lingual communication. And the moment you cannot tell them apart, you achieve AI. I would say that this is really a trap because when we scientists and engineers build systems, very rarely we meant it for beating a particular species, or achieving a certain state of the reality. We want to solve problems. For example, if you build a car, you build an aircraft, it will be very lame for you to claim that my goal is to beat a human in running or beat a bird in flying, right? You actually want something more functional and more measurable. And that basically already, hopefully encourage or motivates people to think beyond this Turing test. And in that sense, the target seems to be pointing to what capacity and what utility you want to build out of the system. And also, hopefully in that vein, you can rethink whether the system really is heading toward having morality, having agency, and having free will, so that we can be so scared to stop developing that. On the other side, more than the Turing trap, there's another trap I found it's also more serious and interesting, which I call the Kant trap. It is related to how we build systems and how we implement systems. Over the past 300 years of a civilization, we become almost religious and dogmatic about Kantianism, which basically highlights the importance of reasoning above everything, right? So we like first principle, we like clarity and causality, and we reach a tremendous height in physics and many other sciences where we can just sit in home and calculate a few equations and we will predict the position of celestial body and so forth, which leads to such a pride in human civilization and the human being. For example, there is a famous conversation happened right here in France between Napoleon and Laplace. Napoleon asked, hey, do you really need the mentioning of a god in your system? And Laplace proudly answered that we don't need that assumption. So basically, there is a belief that with first principle and with science, we can solve everything in universe, if now, but then sometime in the future. Then comes to some other little, what we call the little cloud in the air, which occludes some of this global glorious vision. For example, is causal reasoning really true everywhere? There are a few cases, in fact, they were challenged. You all heard about the general theory of relativity. One of the bigger consequences of that is that you may be able to do time travel. And when you do time travel, the causality kind of argument becomes shaky, right? And also evolution is not about causality. In fact, Mother Nature never evolved species toward a certain goal by designing the best possible mutation, by having the best possible protein design to achieve certain functions like catalyzations, right? It is through random mutation, and there is a selection force, which is rather indeterministic at the macroscopic level. And quantum superposition, which was reflected in the Schrödinger's cat story, same thing. Even the natural world is no longer exists outside of a human mind independently. Depending on what you observe, you may have different physical realities. And there are also incompleteness in mathematical theory about coexistence of consistency and correctness. So all this basically push people maybe to give a opportunity to think beyond using only first principle approach. I think AI is one of these examples, or maybe a good examples. We still don't know exactly how AI system work to the last level of details. All we can say is that there are certain principles being followed, such as using large models and large data, which was missing from this older version of the slides. Self-supervised learning has been pervasively used, and it is building task-agnostic representations. That's very important. AI systems nowadays is not built toward a single task, but a whole collection of different capabilities, and so on and so forth. In the theory side, we actually don't have a clear idea about what is happening. They may learn a manifold, which relies on geometric theories. They may learn a distribution of the data and the phenomenon, which of course draws in probability theories. They may do compression using information theoretical operations. We don't actually know for sure, right? But without knowing this, can we make progress? What the goal is, the answer is yes. People actually set goals for building systems and were able to make tremendous progress even before we know all the details. And that's very unique in AI, unlike what we see in physics and other science. Talking about the goal. Setting the goal itself is actually a very interesting problem in AI, and which actually helps people hopefully to demystify a little bit what is LLM doing and what it cannot do. We all have goals in our life, and you can translate them into executable goals for systems. And here you can even write down into tiers in the form or in the level of difficulties. And here is my pyramid of capabilities, starting from read and write, and then do some reasoning, do some planning, and acting in the real world, and so forth, right? You can define tasks to now make all these capabilities measurable. And that's how engineer came down to the problem. rather than from the first principle and from a theory. And that leads you to start building solutions in the form of what we call models. And that's where you see actually where LLM stands. LLM is actually at the bottom of my task list. They do very well in writing and reading and maybe also speaking. But the question is that can they go even above? Or can we assume that they naturally already achieve everything above? Okay? And that basically is a question valid for measuring and calibrating every model we are building. So that leads to what is language model. Well, language model, to a technician, to an engineer, it is a system doing just one thing, which is the next word prediction. Okay? And through that operation of next word prediction, you get all the user experiences, fascinating experiences, answering your question, solving math puzzles, and so forth. But it is not directly automatically translates to understanding, the content, and also, maybe interact with the real world. In fact, it may just be very, very intricate string matching based on a vast memory of remembering all the word knowledges. Likewise, you can make the same assessment about a large visual model. People obviously wonder, do they really understand the word? Do they really reason, or it's just a word or pixel manipulation? But you can think the question from a different angle. Do this matter? Why do you even build this system for? Do you build a system in order to understand the content, or do you build a system to solve problems? Right? And that's why we got this quote from the famous statistician George Box. He said, all models are wrong, but some are useful. If you think from a utilitarian point of view, maybe there is a more pragmatic but actionable approach toward AI systems. For example, we may ask what LLM is not able to do these days. Well, if you ask the LLM to teach you how to swim, to actually navigate you the traffic, they may have an issue because many of the skills that we human beings have, are not best expressed in the form of language. Just like pouring a water, you don't write it, but you watch a video, you know how to do it, right? And there are also a lot of contents that stay outside of the textual literature, and that already sets the limitation about what you can achieve in large language models. And I believe, people knew it, but people just don't, directly connect to the fact that large language model is not there to give you a, understanding the way we human defined it. Right? In fact, the space where large language models, are doing their work is a very small one in our universe of possibilities and reasoning. And here you can see what's remaining. Right? For example, we have, the space of real-time and space, and the multi-agency with other people, and the law of natures. All these, don't be surprised that they may not be handled by large language models. But we don't call large language model stupid because they cannot do it, because they were not even made to do that. Right? So in that sense, I want to continue with two examples about what I see to be the future of this AI movement in terms of exploring more space of possibilities. The first one is a agent and a word model, which can help us simulate a cognitive and behavioral activities in the real world. What is a word model? Well, the word model, there are many definitions. One famously defined from Professor Yang LeCun in his seminal articles. And here is my definition. It's a simulator of both the physical world, the emotional world, embodied experience, social experience, and all that. That's basically making up the world you are living in. And imagine that you have a model that can produce contents in all these. Then you literally have a word at your fingertip in the digital form. And how to make that is a technical design, which I'm going to browse away, but they involves, of course, ability to process sensory data, long memory, and ability to persistent memory, and also carry out objective-driven architectures and so forth. Right? But the biggest value of having a word model is to allow you really do reasoning among a bigger space of possibilities. There are, a different way of defining reasoning. We thought that our reasoning is about finding the shortest path toward our goal or finding the optimal solution to a task. But every one of us probably, from time to time, do something called a thought experiment, which means hypothetical thinking. You just simulate outcomes of potential solutions, and you pick the best one, right? And that's actually, a very intuitive way of thinking about reasoning, which is less, elegant and mathematically rigorous, but it works. And here is what a word model can enable you. It defines you, a oracle which simulates the next state of the word given the previous state and the action. And this little equation, if you just expand the scope of the possibility and the content, can help you do a lot of things. For example, you can set up your goal, and then you can just do forward simulation by drawing samples, from this distribution or this generative model. And then you have multiple pathways toward the goal. One of them probably is hitting your goal. Others are getting closer or further. And then you can choose the one that is best for your fit or in your budget. In fact, the AlphaGo is an implementation of this idea. It is simulating multiple moves from a particular board position, and then using a Monte Carlo tree search to find the optimal one, and then execute it. Right? You can imagine that now my situation is not the board position, but real-world problems like a traffic in autonomous driving, like a battleground configurations, or maybe something you never experienced before, like how to colonize on Mars and so forth. And you can use the same idea of simulative reasoning to solve many problems. And that's actually what the word model is about. I'm not sure this video is playing. Oh, it is playing. Well, this basically is a video showing you how we might be able to qualify even the quality of the word model by measuring or testing its steerability. Because the word understanding is not very well defined. It is a very subjective opinion or maybe capability for human, but how a word model understands the word? Well, what if you can tell the word model to do things you like, steering the car and moving the objects and real-time instructing a particular behavior, and then the word model execute? That probably gives you a hint about how word model can understand the real world. Right? You can also put the agent into the word model because many word models these days are being equivalent to generating videos or generating 3D contents. But that's not really all the possibilities in the world. The real world contains people. Therefore, agency and our agents can be another content inside the world. And then they collectively generate signals into your artificial brain. And then over there, you can have a thought space, doing hierarchical embedding and putting back the responses, making recommendations of actions and so forth. So this is a direction we see to be highly promising and important for the AI to go beyond the large language models. And here is a sketchy of a potential architecture design down the road where the word model, which is a bigger version of the large language model built on multimodal data, can be itself a module inside an agent model, along with other representations like the goal, the belief, and also the plans, and also interface with the external tools and other things. You can even build a community, as Mike mentioned, or a collective group of agents, which gives you this more collective behavior in an abstracted way. Then you have super agents, which can make macroeconomical or societal decisions based on the situations. Right. So again, I couldn't play this movie, I guess. And what is happening here is that I want you to imagine what an agentic and a physical world look like. Oh, it is playing, right? It is actually not what you see in Sora and in Gemini 2, or Genie 2, where you see cool, visual effects and the cool, movies and the 3D renditions of the reality. Agentic world is a world that you experience in real life, where this particular guy, you can see that he is running, he actually is interacting, with the object, inside the world. Imagine that when you drive, if you treat the coming car as an object versus you treat the car as an agent, which has its own plan, its own intention, I bet your behavior will be very different. You may run away from it, you may stop, you may just go head on. Who knows? But if it's an object, you don't actually feel that complicated to avoid traffic, right? So that's basically what I see to be a promising direction, an important one down the road for the AI system to go beyond LLMs. I want to have a word about whether we should be afraid of this or not. There are a lot of discussions and speculations about the AI system become so powerful that it come after people and kill people. Well, this is more than just a sci-fi. In fact, I didn't see people seriously establish hypotheses and proof or evidences of substantiating that statement. And here, I want to add my thoughts. I think when we talk about agency, free will, moral, and drive, it is a different space than having a task and solving it. It is not very clear yet, our current architecture even have room to accommodate this kind of capability, and also what kind of data, what kind of task, can be used to attain that kind of capability. So I think maybe it's not impossible, but we're not so close to reaching that state yet. To close this part, let me try to expand the space of reasoning even further a little bit, which is in the physical world. And that's where, again, AI can provide huge value than we already experience now. For example, talking about the problem in biology. Well, biology is a fascinating field, but a very, very classical one. Medicine, human health, in fact, is a biological problem because when you see, say, an organ failure, it's more than just going to the department of liver or brain and get your MRI scan and then take some medicine. You may want to even look into the cellular level lesions of your tissue, your DNA mutations, and your hereditary histories and so forth. All this information provides you a holistic picture about what disease is about. So it is biology. But understanding biology is very complicated. It is a multi-skill subject, go all the way from nanometer microscopic events to macroscopic events in the order of this size, right? And in the past, without the right tool, we take a sliced approach, using data collecting at certain resolution and using models only focusing on one, say, well-defined problems. And these are the tools we use, right? And it is not working very well. That's in fact, we still, don't understand very well about biology. And designing a drug and treating a disease still is difficult. But nowadays we have better models, or maybe more powerful models. What's the implication? For example, we see one implication already, right? You can now solve this puzzle of protein structure like we never did before in a very, very efficient and accurate fashion and very fast. And it's important to remember that AlphaFold 2 does not understand the law of physics. Okay, it is a purely data-driven approach that gives you a input-output mapping between the sequence and the structure by training on many collection of large data. And it's a very different approach, an empirical one, an empiricist one, against the first principle one in solving a big piece of puzzle in science. And it is recognized by a Nobel Prize. And these two contrasts is very, very important to recognize because first principle approach, however elegant it sounds, it gives you uncertainty of quantification of uncertainty, clarity, explainability, but it is not scalable to many of the problems we want to solve even now. Whereas the AI foundation models gives you that capability in terms of the outcome, even though it is not quite satisfying all the scientific curiosity and also the clarity and the causality. But I think there is a middle ground that we can live up with both and let the two approach to naturally merge rather than waiting with each other. So in that vein, there has been a lot of amazing developments in the past several months, in fact, using foundation models in biology. And this is one effort I want to highlight, which is called an AI-driven digital organism, which is not about just building one model for one type of data, but building a cluster or system of models that covers different aspects of biological data, from DNA to RNA to protein to cell to tissue and to phenotype. Why this is possible? Well, because we see similar things are happening already, in our cognitive space with language model merged with the visual model, now with audio models and so forth. So multimodality is no longer a hurdle. The fun part is, of course, is to find the right representation architecture for unique biological data that is different from the human language and the visual. But this is an ongoing research which I believe to be very, very rewarding and interesting. And our approach is to take a divide-and-conquer approach to build smaller models from ground up, and then try to really connect them together through, for example, hierarchical embedding, through cascading of information, and the conditional generation and so forth. They have all sorts of techniques being developed and to be developed to make use of the models in a collective way. And then you can harmonize them, hopefully, to achieve higher predictive goals, which can simultaneously, for example, predict interesting queries from all different levels, all the way from drug design to simulation of cellular environment and the treatment effects. I think this vision is going to be disrupting the science of biology in a tremendous way. Right now, the field of biology are still primarily relying on wet lab, physical experiments, and trial to make the discovery, to confirm the discovery, which is a very expensive thing. And with imagine a digital organism which can simulate all possibilities of biological world, what you will probably do is to use the simulator, the AI system, to first do the exploration, right? To weed off the low probable hypothesis, and only output the most probable ones, so that you can do only a few wet lab experiments, to validate. And this is getting the biological science closer to what we do in other places, where such as power plant design, chip design, relying heavily on simulation and computing instead of trying a physical production to explore all possibilities. So I think there is a potential for such an AI-driven digital organism to be a new paradigm for in silico biological research, just like what we do in other disciplines and science. So here are just two examples I want to share with the audience about how AI may evolve and develop in the next couple of years. And I want to close by making the following remark. Scientists are supposed to be open and also undogmatic. But it turns out that in the past several decades, we scientists ourselves become rather dogmatic about the approach we take. We become less skeptical about the science itself, right? And this is actually probably a side product unexpected from Kantianism, because reasoning and the first principle makes you feel so powerful and so satisfying, whereas humanists who rely on empirical evidences, and having skepticisms, for almost everything, makes people less confident, makes people feel unsafe. But I think with the advancement of AI, which builds on large model, the progress and the outcomes, the engineering products, are maybe for the first time in history dramatically outpace our ability to understand every fact and every theory behind the finding. So should we stop and wait for the theory to catch up, or should we carry forward the experimentation, to advance the science, and at the same time, doing the understanding simultaneously? This is a good question we should all face as scientists. So I want to conclude by one example, which again come out of France. Dr. Pasteur, who invented the vaccine. Can you call them a Kantianist or a humanist? I don't know. But one thing I know is that by the time he invented the vaccine, we don't have knowledge about DNA. We don't have knowledge about protein. We have very little knowledge about the cell, right? Therefore, that discovery of a vaccine getting people immune to infectious diseases is a pure empirical finding, and it was adopted and accepted through very rigorous tests. And that ended up saving millions of lives. I think we are at the same moment right now in AI, where great inventions and great capabilities are being presented. It is us to decide how to mitigate the risk, but also how to balance the speed of innovation in that direction versus being cautious and being risk avert to impose strict regulations about what we are doing. So with that, I want to go back to my first page where outline the future of AI in the next few years. I think the major mission that we want to push forward, including within my own university, is to deploy AI in the larger space of possibilities for reasoning, and then find solutions to make that happen, and also implement solutions to drive capacities and needs in human society. With that, I want to conclude my talk, and thank you very much for the attention.